Hello everyone. In today's video, we're going to talk about concavity and the second derivative. So, what is concave up or concave down? So, when you see a function, look at these two. They're both increasing function, right? So, what's the differences between these two increasing function? Well, in these two functions, they're both increasing, but the first function, they're pointing down, right? So this is concave down, and this one is pointing up, more like opening up. This is concave up function. So what determines the concave up or concave down? Well, it's the second derivative. So here is our first note. The first derivative tells us the function increasing or decreasing. If it's a positive, that means it's increasing. If it's negative, that means it's a decreasing function. And then the second derivative tells us if a function concave up or concave down. Okay, so what is second derivative? Basically, is you take the derivative of the first derivative. So if we use a prime notation, so remember our first derivative. It's going to be f prime x, right? Or we use y prime. So the second derivative is going to be double prime f double prime x or y double prime. So if we use another notation, remember the first derivative notation could be dy over dx or dfx over dx. So for the second derivative, there will be dy second derivative over dx squared. That means the second derivative of x. Or they can also write it as d square dx square fx. Either way. So this is the notation of second derivative. So if the second derivative is positive on an interval, so the graph of y, the original function, is going to be concave up on that interval. So we can say that f is increasing or decreasing at an increasing rate. I'm going to write this down. So for the second derivative, if the second derivative is positive on an interval, then we can say the graph of y equals to f of x is concave up. On that interval. We can also say f is increasing at or decreasing at an increasing rate. Oh, here is very important. First of all, the second derivative is not determining whether the function is increasing or decreasing. As you can see, so now let's take a look. What does the last sentences mean? If x is increasing, then x increasing rate. So take a look at here. This is a concave up if it's going up. This is concave up if it's a decreasing function. That means on these both functions, they can be increasing. It's an increasing function. This is a decreasing function. But they're both concave up, right? So that means they're increasing or decreasing at an increasing rate. That means the speed that they're doing is faster and faster. Okay, so similarly, if I change these two, if this is a negative on a certain interval, that means this is going to be concave down. We can say a function is increasing or decreasing on a decreasing rate. So that's similar, just opposite. So now let's try to find the second derivative. For example, I want you to find the second derivative for fx 3x to the 7th. So in order to find the second derivative, the first thing is you need to find the first derivative first. So the first derivative is what? Well, the first derivative is going to equal to 3 times 7x to the 7 minus 6, which is 6. So this is 21x to the 6th. Okay, so from the second derivative, you're going to take another derivative from this first derivative, which is 21x to the 6th, and then you take derivative. That's second derivative. So this is equal to 26 times 6x to the 6 minus 1, which is 126x to the 5th power. So that's second derivative. So in an application problem, such as the height of a particle, at time t, f of t equals to t to the q minus 4 to the t squared plus at. Okay, so I want you to find the height, velocity, and the acceleration of the particle when t equals to 0, 1, and 2 seconds. Okay, so for the first one, finding the height. So they're given you a function. This function is function timed of a height. It's a function height, a height, function height related to the time, right? So you're given the time and you found the height. So when t equals to 1, we just need to substitute f of 0. Substitute f of 0 into the original function. So you will get 0 to the cube minus 4 times 0 to the second power plus 8 to the 0, which is equals to 0, right? So that means the original height is on the ground. Very easy to understand. So what about after 1 second? Where's the particle? Well, we substitute 1 into the original function because this function, the output is going to be the height. So I got 1 minus 4 plus 8, which is equal to 5 feet, right? So after 1 second, the particle is 5 feet from the ground. Well, we substitute into 2 into the original function. I have 2 to the cube minus 4 times 2 squared plus 8 times 2. This is equals to 8 feet. So that means after 2 seconds, the particle is 8 feet high. Okay, so the second thing they ask you to find is the velocity at the time at 0 second, which is the original places, and after 1 second and after 2 seconds. Well, how do you find velocity? That is our first derivative, right? Well, you take the first derivative of the function. So I have 3t squared minus 8t plus 8. This is your second derivative, which is the velocity. So I substitute 0 into the function. I will get 8. So what is that's very important. When it comes to the second derivative, you need to know what is the unit. Well, remember the first derivative, how do you define the derivative? Is the changing in y over the changing in x, right? So y, what's the unit in y? It's the feet. Well, the changing in x is what? It's the second time. So that means it's feet per second. So that means at beginning, the initial velocity is 8 feet per second. So at the first second, so the velocity is going to be 3 minus 8 plus 8, which is 3 feet per second. Okay, at the second second, this is equals to, you substitute the function for the first derivative, you will get the velocity is equal to 4 feet per second. So at each of this time, the velocity is a positive, and the particle is moving upward, increasing in height, right? Because they're all positive, that means the graph is going to be up. Okay, last part is the acceleration. So how do you find the acceleration? Well, if you think about what acceleration is, it's going to be your second derivative, because the acceleration is the rate of change of the velocity, right? So that means the second derivative is going to be our acceleration. So to find the second derivative, we need to take the first derivative, another derivative. Because this is our first derivative, we take another derivative of the first derivative. So I have 6t minus 8. This is our second derivative. So this is also our acceleration. Okay, so now let's take a look. Well, for this part, I have f of 0 equals to 6 times 0 minus 8, which is negative 8. If it's negative, this is going to be what? Concave down. That means at beginning, the acceleration rate is going to be at decreasing rate. The velocity, I should say, the velocity rate is going to be decreasing, which makes sense when you try to shoot something out. Usually, your initial speed is the fastest, and then because you have some resistance in the air or some aerodynamic, whatever that is, I don't know that much about physics, so it will slow down the speed, right? So it makes sense when it's decreasing. So what would be the unit? So you think about this is going to be the changing in the first derivative over the changing in the time, right? So I substitute those unit into it and check. So the unit of the first derivative is going to be ft divided by s. And then the time x is represented as the time. I should use t instead of x. And here to time. So that means this is going to be feet per second square. So that will be the unit of the acceleration. Okay, when it's 1 second, this is going to be 6 minus 8, which is negative 2 feet per second. Still, this is concave down. Well, at this 2 second, I have 6 times 2 minus 8, which is 12 minus 8. This gives you 4 feet per second squared. So what caused that happen? Well, if you think about you shooting something in the air, the trajectory is, here's you shooting something in the air. This is the ball. At beginning, your speed going up, 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 up. When reach the maximum height, you're going back down, and your speed up because the gravity is helping you, it's doing you a favor. So that's why after you reach in the height, the vertex, I'm sorry, what's that called? The peak, after you're reaching the peak. So your speed is going to slow down, but your acceleration speed is going to speed up. Okay, so in general, how do you summarize these, what happened in here? So at time 0 to 1, the acceleration is negative, so the particle's velocity should be decreasing at those points, right? And then the particle was slowing down at time after 2 seconds. The velocity is positive, so the particle is increasing in the speed. Okay, and now the next concept is inflection point. So what is inflection point? By definition, inflection point is the point on the graph of a function where the concavity of the function changes from concave up to concave down, or the other way, from concave down to concave up. So for example, look at this graph. So for a cubic function, this looks like this one, right? Y equals to s to the cube. So the concavity is going to change. Here, before 1, this is concave down, right? After the origin at that point, the graph becoming concave up. So this is the inflection point. So now take a look. A parabola like this. Is there any concave inflection point? No, the function, yes, is from decreasing become an increasing function. But for the function itself, the concavity is going up the whole time. It's always concave up. So that means there's no concave down, right? So that means there's no concave down. The concavity doesn't change. That means there is no inflection point. We can also find the inflection point by calculate the second derivative. Remember, for the second derivative, if you concave down, the second derivative at here is going to be negative, less than 0. And then the concavity is going to change up, so that means the second derivative is going to be a positive number. It's going to be greater than 0. So that means at inflection point, the concavity is going to be 0. Okay, so that's it for today for the second derivative and concavity. So let me know if you have other questions.